Welcome back to Applied Mathematics. In this video, I want to introduce you to function notation. The idea of function notation is one of the most powerful tools in the mathematician's toolbox. It's a very general tool, which means that we're only going to be scratching the surface of what you can do with it in this course. That said, I really do want to give you a broad feel of the kinds of things that you can do that you might be interested in looking at further as you continue your studies, whether in mathematics or outside of it. The mathematical tools for function notation are all relatively straightforward and by and large things that you've already done in other contexts previously. There's not a lot new that we have to talk about for function notation, which unfortunately means that it's going to be a pile of vocabulary. Let me get my head out of the way and we will get started with the big one. A function is a rule which maps each element of one set, which we call the domain, to exactly one element of a second set, which we call the range. Keep in mind that the idea of a set itself is an incredibly general term in the language of mathematics. A set is a container that holds stuff. We don't care what kind of stuff it is. In this course, we have dealt with sets of numbers because, well, they're the easiest ones to deal with, but that doesn't really mean anything. And so with that in mind, we can have our functions acting on any sort of thing we would like to. For example, I might devise a function. The notation here is not that important, but it's relatively common, so I want you to at least have seen it once. But we're going to name our function f. We're going to put a colon to say we're defining function f. And we're going to say it is a map from a set of letters, that will be the domain, to a set of colors, that will be the range. All right, so we're going to feed the function letters of the English alphabet, and the function is going to spit out a color. Very often we can define a function like this using a table. So maybe I will call the letters that we feed into the function x, and then the output we're going to get, we're going to use this notation. F, opening parenthesis, the thing we're feeding in, which is x, closing parenthesis. The notation here tends to look like multiplication, but it is not multiplication. This is what's known as function notation, f of x. So we just start listing out some letters. All right, we have the letter B. I don't know, maybe that stands for blue. We have the letter G. Maybe that stands for green. The letter R will stand for red, and the letter Y will stand for yellow. Right, there's a couple of colors taken care of. There are many, many other colors. So maybe we want to modify our function a little bit so that there is some letter we can put in to get out black. Notice here we can't use B as the key to get out black because we already defined B as going to blue. And the rules of functions say that there is exactly one element in the range for each element in the domain. B goes to blue, we cannot also have B go to black, so we need a different letter to go to black. I don't know. How about K? That seems reasonable enough. I guess we could have used L, but I don't know. K just seems a little bit nicer. And then just one more for fun. How about gray? Again, we can't use G here because G goes to green. So the first letter is out. We can try the same thing we did with black. Well, let's try the last letter, K. So in gray, the last letter is Y, but we've already defined Y. Y goes to yellow. So that's out. We can't use R. R goes to red. So maybe E? E is gray. That doesn't really make a whole lot of sense, but we're kind of out of choices, so we have to do something. Is this function actually useful? I'm sure to someone somewhere it's an incredibly useful tool to be able to have a couple of commonly used colors, each one represented using a single letter so that you can quickly spell out things that you're trying to do with colorations. Mathematically speaking, it's not that interesting of a function though, because, well, you can't do anything to get to it, you can't do anything to get from it. But like I said, I wanted to use this as my first example because it gives us this general feel of what you can do with a function. The idea of a function is incredibly broad. So, just continuing on with the notation here, I've listed out in a table the definition of the function. To actually use the function, you would write down the letter. So we have that letter F. I'll need my head out of the way so I can actually write things in. And instead of writing f of x, you would write f of the input, the domain value. So just picking one of these at random, f of y. The table says when you have x being y, f of x comes out as yellow. So f of y is yellow. And f of e is gray. So on and so on. For the rest of this video, I'm going to be focusing on what are known as algebraic functions. And I want you to think of an algebraic function as a name given to a particular expression. And then in the not too distant future, I'm also going to introduce you, we'll get a couple of chances to play around in this class, with what are called transcendental functions. And a transcendental function is basically just anything else. Anything that is not an algebraic function and it's acting on real numbers is known as a transcendental function. So a classic algebraic function, we define the function. I've already talked about f of x, so just continuing on in the alphabet, my next letter would be g of x. And then we write out some expression involving x. 2x squared plus 3x minus 5, maybe. All right, so this is a polynomial function. It is defined for the variable x. And I think that this gives a good sense of why functions can be useful. In the past, you've grown accustomed to using variables as a shorthand for numbers. Sometimes numbers you don't know, sometimes just numbers you don't care to write out. Right? For example, the character pi used for the circle constant, 3.14, etc. Or L, the length of a rectangle. We don't know what that is, but we can put a placeholder in and we can work with it. We're going to use function labels in much the same way. All right, so g is the name of a function. In this particular example, it's this expression 2x squared plus 3x minus 5. And in this video, in this course, we're going to be using that as a shorthand for giving instructions. The same way we might give you, evaluate an expression when x has this value as one of the first things you did with variables. Well, we can evaluate this function as one of the first things we do with functions. As you continue onward in the study of mathematics, you can unlock more and more powerful things to do with it. All right. But the first thing to do with it is to evaluate. And the notation we use here might say something like g of 3. So just like the example with the table, we had an x, we've replaced it with 3. And so we look at our definition of our function, we look for every place that has an x, and we replace it with 3. Evaluate the expression for this particular value of a variable. It's something you've done many times before. It's just a different way of notating that instruction. All right, so 3 squared is 9. 2 times 9 is 18. 3 times 3 is 9. 18 plus 9 is 27. And 27 minus 5 is 22. Absolutely, I could have done that whole thing with a calculator, but I don't have my calculator in front of me, so that's out the window. And just like any other variable expression, you can evaluate a function at different points to get different results out. It might be important to evaluate g of negative 2, which would be 2 times negative 2 squared plus 3 times negative 2 minus 5. And going through the algebra there, the arithmetic relatively quickly, I get out that this function g at negative 2 has a value of negative 3. One of the things that we can do with functions to make them a little bit more complicated than just evaluate this expression is introduce what's called a piecewise function. And so let's see, we've done f, we've done g. I guess I'll use h of x as this example. And to define a piecewise function, we're generally going to put something like curly braces, and then we'll have a couple of lines. So maybe we have 3 over x minus 5, and we have how about, yeah, 1 should work. So we have 2 different rules going on here, and that can make things a little bit confusing. So what we do is we introduce another column, and give instructions. So h of x is 3 over x minus 5 if x is less than 2, and h of x is 1 if x is greater than or equal to 2. That way, we can put in a value. I said put in a value, and then I didn't put in a value. Say h of 0. Well, looking at the two rules, 0 satisfies x less than 2, not x greater than or equal to 2. So when we plug in x equals 0, we look at this expression. 3 over 0 minus 5, which is negative 3/5. If we plug in something else, something like h of 3, well, in this case, when we look at our conditions, it is not the case that 3 is less than 2, so we can't use that rule. It is the case that 3 is greater than or equal to 2. So we can go ahead and use that rule, which is a very simple rule, and just says, oh, the function gives you 1. I don't care what you put in, the function gives you 1. There are a couple of ways that this sort of rule can be useful. In a physical sense, you can be looking at a situation that does change. For example, maybe you are trying to write out an equation for the force being provided onto an object from a magnet. If you are in the area of space where the magnet is exerting a force, well, then you have something. And if you are away from the magnet, maybe we can say that there is nothing there. So in certain places you have a force, in certain places you don't. You split up into a piecewise function to say, yes, here we have this, here we have nothing, here we have something else. So there are certainly physical applications where this is incredibly useful. This is not a physics class, though. This is a mathematics course, so we're going to be looking at a much more pragmatic approach to what's happening here. If you look at that expression, 3 over x minus 5, one of the things that I hope you notice without too much thought is that it would be a problem if we plugged in x equals 5. If we plug in x equals 5, we get 3 over 0, and 3 divided by 0 is undefined. So we can use a piecewise function as a way of avoiding problem spots. We can set up a function, and we know that if we get too close to the problem points, bad things are going to happen. So we just tell the function to shut down. We tell it to stop thinking about it, ignore that, and do something different when you get too close to the problem point. That way, nothing breaks. Right. The last thing here we said that the domain of a function was the input values, and the range of the function was the output values. And we just saw that if we look at something like f of x is 3 over x minus 5, you try to plug that in, you get out nonsense. So there is an input value of 5, but the function does not have an output value. And the rules for functions said that every input, every domain element, had exactly one output range element. And so we have something that is called the implicit domain convention. The implicit domain convention tells us that for an algebraic function, the domain is the set of all real numbers which provide a real output. So in our case here, f of x is 3 over x minus 5. We know that if you try to plug in x equals 5, bad things happen. So we can say that the domain is the set of all values of x such that x is not equal to 5. So formally, technically, it should be the set of all values x such that x is not equal to 5. But I'm lazy, I'm going to use shorthand, I'm going to ignore the fact that this is a set because, quite honestly, that rarely comes up as being something that's important. One of the places that you have to pay attention to when you're trying to think about the implicit domain convention is dividing by 0. If you divide by 0, bad things happen. You don't get a real number out. So dividing by 0 is something outside of the domain. The other operation that can be problematic is the square root. If you take the square root of a negative number, the result is an imaginary number, not a real number. And the implicit domain convention says we need a real output. So because the square root gives us an imaginary output, the square root cannot be evaluated at a negative number in a function. Those are the two things we look for. And those are really the only things we care about. So if I have something like g of x is 7 over the square root of 9 minus x. 9 minus x, not 9 minus x squared. Sorry about that. Well, in this case, we have both issues. To determine the domain, I know that the square root of 9 minus x has to not be 0. And I know enough about the square root to know that the only value where you take the square root and you get out 0 is 0 itself. So that means that 9 minus x has to not be 0, which means that 9 has to not be x. The other thing I know is that the stuff underneath the square root has to be positive. 9 minus x is greater than or equal to 0, which means that 9 is greater than or equal to x, or the way we more normally write it, x is less than or equal to 9. But then combining in what I already said, that x itself cannot be 9, it's not actually the case that x has to be less than or equal to 9. All told, the rule has to be that x is strictly less than 9. Right. So thinking through how you can run into problems in an algebraic function and listing them out is an important step. Right? For our purposes in this course, just doing that is going to be the end goal because, well, it's new and it's challenging enough. But again, I want you to keep in mind that idea with the piecewise functions from earlier. If you know where the problem spots are and you are designing the function, you can map around them. You can find some way of saying, no, this is not where we need to be, and reacting accordingly. Or, sometimes more importantly, you can put a safeguard in place. Right? If you are designing a computer or a robot that's following computer instructions, the computer is going to provide the robot with a function. And if you don't put safeguards in place, bad things can happen. In the days of the early mechanical calculators, devices that would do calculations by spinning gears around, there was a well-known issue of dividing by zero. If you told the calculator to divide by zero, it would not realize that it was a problem, and the gears would start spinning. And they would keep spinning. And there would be nothing to cause them to stop spinning until you disconnected power from the machine. And then, once it was safe to go in there, you had to manually reset things, because if you plugged it back in, the gears would start spinning again. So, those sorts of things, knowing where the problems can happen, putting safeguards in place to avoid them, is where you will go from here. Right? Depending on your career path, depending on the program you are studying, what that's going to look like is going to change drastically from student to student. All I can do is give you the basic tools, the basic way of thinking about this could be a problem, and some vocabulary to help you communicate it. The last thing that I want to do in this video is look at the graph of a function. You might see instructions that tell you to graph function f. Or maybe if they're feeling charitable, they'll tell you graph function f of x. This is absolutely equivalent to saying graph the equation y equals f of x. But compared to just graphing an arbitrary equation in two variables, the fact that it is a function gives us an important piece of information. I know that as long as I pick some unique values for x, I'm never going to run into issues. In general, it's possible that I could try to pick a value for x and end up with having to make a choice. But if I had to make a choice, then the thing I have would not be a function. Right? The rules of the functions say that for any given value of x, there is exactly one value of y. For any given value of x, there is exactly one value of y. So if I pick values of x to plug into the function, each one is going to give me exactly one value of y. And I know I will be able to safely graph the function. Consider as a counterpoint this graph of an ellipse. This can be expressed as an equation in two variables. The hows and whys are beyond the scope of this course, but if you use numerical graphing software and you try to graph something like x squared over 25 plus y squared over 9 equals 1, you will get a graph that looks something like this. This graph is not a function because if you pick certain values of x, there are two different y values that could possibly come out. Thinking through a graph like that is known as the vertical line test. The vertical line test is almost always expressed by saying that no vertical line can pass through the graph of a function more than once. Although I absolutely hate that phrasing of it because it completely masks why the vertical line test is useful. The vertical line test cannot be used to tell you that the graph you are looking at is the graph of a function. The vertical line test can only be used to tell you that the graph that you are looking at cannot be a function. This graph cannot be a function because this vertical line passes through the graph twice. For the sake of time, I'm not going to go through an example of actually graphing a function by plotting points. That is something that you've seen in previous lessons already. Instead, what I do want to do is remind you that computer graphing software exists. Oh, every button but the right one. Here we go. I am now on the website Desmos, desmos.com. You can see that I have typed in the function we were looking at earlier, f of x equals 2x squared plus 3x minus 5. And by typing that in, the graph of the function appears. So numerical software is really good at graphing functions. When you have things that aren't functions, it can be tricky. Sometimes the graphing software can handle it, sometimes it cannot. But for right now, just a reminder that this is a thing. You can mechanically choose points, plot the points, and connect the dots to get a curve. Computers can do the exact same thing, but an awful lot faster. I think that's far enough to go in this video. I've been talking long enough, so I'll wrap up with that. Thank you as always for joining me, and I'll see you in the next one.